All right, so I will resume, and so what we're going to talk about is, efficiency. That little part of the video will be gone. Tic-Tac-Toe, hustler. This is going to be skills for something like that. How many of you have heard of number bonds? So this was, how many ways can you write 10 as the sum of two non-negative integers? So, all these decompositions. So we can write 10 as 10 plus 0. We can write 9, as 10 plus 0. Or we can write it as 9 plus 1. Eventually we get to 5 plus 5. Then we get to 4 plus 6, all the way down to 0 plus 10. So how many of you have seen something like this? Okay. And so I'm using 10 because that's what I saw in my son's class, and so that's the number I know. Natural question might be, why do we care about something like this? What are the building blocks? What are our rules as to what we can use as the summons? And so here, do kids know about negative numbers? If they do, you could actually expand this and say, well, we could actually write it as -1 plus 11 and get into the concept of, there's infinitely many things if you have strong students like that. Let's just leave it like this. So to me as a mathematician, the most interesting thing for me is asking questions. And so when I see something like this, what are natural questions that can come to mind? One question is, how many ways can I write 10 as the sum of two non-negative integers? So number of decompositions of 10 as a sum of two non-negative integers. And you see we've got to be very careful here in our phrasing. It's not enough to just say it's the sum of two integers. Do we allow 0 or not? Does order matter? Are we considering 4 plus 6 different than 6 plus 4? And so there's a lot of great stuff you can begin with here already. So can somebody tell me how many ways we have? 11. So if we use zeros are allowed, and if we say 6 plus 4 is different than 4 plus 6, there's 11 different ways of doing this. If I replace 10 with 5, how many ways are there? 6. So then the question becomes, can you sniff out the pattern? And so, especially if you're teaching in an early grade, I find, with my son, the notion of a variable is very difficult. But we can start making a little table. And so we could have, and this is, a good way to introduce almost some statistics. A number, and then the number of decompositions. And so if we start doing this, we can start filling in the table. So if the number is 0, there's only one way of doing it. If it's 1, there's 2 ways of doing it. If it's 2, there's 3 ways of doing it. And the students can see the pattern. And so for this one, I would be pretty confident that the students would be able to quickly figure out what the pattern is. Right, now that it seems to be shaded, I think I can move this back a little bit. Okay, good. All right. Yes?
I just have a quick comment because maybe in kindergarten,
yes.
Kindergarten children in Lexington
right.
have a whole little unit about this.
Excellent.
And the book talks about it's called a sleepover. And
okay.
10 kids are at a sleepover and they have bunk beds. And they rearrange themselves differently on the bunk beds. But there's always 10 kids. And
okay.
They, sort of make a joke and try to trick their, mom. And so they generate all of these things. So, I mean,
wonderful.
It's a wonderful way of putting that in context for kids.
Excellent.
And they start saying, oh, well, there could be 10 on the top and 0 on the bottom. And then one person put them down and then 9 on the top. And, and so it's,
no, and then this is that's wonderful because this is now something as to, why would you be splitting the number in these ways? But there's some dangers here. And, I'm a math professor. This is not a proof. This is a list of a couple of facts. And so depending on the level in which you have the kids, you can say, just because we've detected a pattern does not mean the pattern will persist. Now, what I find when I teach calculus is the hardest part of teaching calculus is people's algebra skills are atrocious. So I just want to see, how good you guys are. 16 over 64, 1/4. 19 over 95. That's 1/5, okay. 49 over 98. 1/2. 12 over 24. I'm sorry? 1/4. 1/4. Oh yeah, cancel the 6's, I get 1/4. Cancel the 9's, I get 1/5. Cancel the 9's, I get 4/8, which is the same as 1/2. So 12 over 24 must be 1/4, right? You know, I've got 3 data points. And so I like examples like this to remind students how important it is to be able to prove something and not just detect a pattern. Step 1 is detect a pattern. You need to have something that you're aiming for. And there's an enormous advantage to having something to shoot for. But just because something has held up for a while does not mean it's going to continue. Football fans, just because the SEC has done so well. All right. So I like to use this as a strong motivation for why do we prove things. And one of the reasons we prove things is we can be misled. And there's a whole slew of examples you can give. You can talk about the following. Here's another one of my favorite sequences. 1, 2, 4. What's the next number?
6.
We'll take the average. It's actually 7 is actually the next number in the sequence. And so what this comes down to is if I give you a circle and you use n lines, what's the maximum number of parts you can divide a circle into? And so if you have just one line, you can divide it into 2 parts. If you have no lines, you have 1 part. If I have 2 lines, I can divide into 4 parts. If I have 3 lines, 1, 2, 3, 4, 5, 6. Turns out that's the best you can do. And this becomes a fun problem. What would be the next term in this sequence? What's a good way to methodically go to all the different possibilities? And we'll get back to stuff like this. I want to return back to the number bond problem. So a lot of you have looked at how many ways you can write 10 as the sum of 2 integers. What's the next natural question you can ask? This is how research mathematics gets started. I am not that smart, but I ask a lot of questions. And every now and then I choose a good question that people hadn't thought of. So you've just done Okay. Thank you. This is why I now wear this on the outside. Project. I'm not optimistic about this technology anymore, unfortunately, because if it's going red that fast. All right. So what's the next natural question to ask after we've figured out how to write 10 as the sum of 2 numbers? So one way is to go to products, but that now introduces multiplication. And if we have kids at the elementary school level, it pains me that my son doesn't know multiplication yet because there's so many things I want to do that I can't. But what would,
Using 3 numbers?
I'm sorry, using 3 numbers. So now, and again, it helps if you can do things formally and write x plus y equals 10. Now we'll move to x plus y plus z equals 10. We're splitting something now into 3 sets. And again, in terms of decomposition problems, it's maybe you have a class assignment and you're looking at how many different ways can I split things up into some people get to do this and some people get to do that. And this would be a great way now where order matters. These are the people who get to go to the Red Sox game. These are the people who get to watch us on TV as we go to the Red Sox game. Something like that in terms of how many different ways can we split. Then of course you can ask more refined questions. Does it matter who is going to the Red Sox game or just the number of people? But So has anybody tried to do x plus y plus z equals 10? Excellent. So we can do now a new problem that you haven't seen before and try to think, how would we build on the unit we've just done? And it turns out these decomposition problems are useful. And I'll get to a little bit later why we care about this. I'm going to assume everybody is at least somewhat motivated because they're here right now. This also leads into statistics. So the 21st century is going to be the century of statistics. When I was a postdoc at Ohio State, I took a data analysis seminar. And I still remember one of the comments. I don't remember who said it, but I at least remember the comment that we have satellites orbiting the Earth, beaming down more information every day than is in the entire Library of Congress. And we have a couple of hours to process this and make predictions on weather. So the question is, how do you deal with such a wealth of information? We need to start training our students in terms of collecting data and making sense of it. So what do you think we should start doing for this problem? Collect data, right? So number, and then number of triples. All right.
We would call this an organized list.
An organized list. See, this is where if I had some formal training, it would be useful. So, okay, so this is an organized list. So if our number is 0, how many decompositions do we have? 1. What if the number is 1? Can we do this in our heads? 3. What if the number is 2? 6. So the way you can see it's 6 is if it's 2, I can have one number is 2 and the other number is a 0. And I have 3 ways to choose which number is the 2. If it's not 2, I can have 2 1s. And if I have 2 1s, that's the same as choosing one number to be a 0. So that's also 3 things. So I can look at the 6 as 3 plus 3. How many of you know your combinatorics, your n choose k? If you know that, you can write the 6 as 3 choose 1. I have 3 places to choose which one is the 2. Or I have 3 choose 2, 2 places to choose 2 1s. All right, well, we've got 3 data points. This is exactly how much we had last time. Surely you can tell me the pattern. So triangle numbers is a really good guess. So what are you guessing for the next one? So there's a beautiful guess. Was this just, hey, I noticed these are triangle numbers, let's hope it works? Excellent. So let's think and let's go through in detail, is this the triangle numbers? So I have 3. I could have the 3, 0, 0 triple, and there are 3 different ways of ordering that triple. I could have a 2 and a 1. How many ways are there to order the 2 and the 1 triple? 6. Because now what's difficult is 2, 1, 0 is different than 1, 2, 0. So,
You also have the 2 above that shows that you did it 6 different ways, right?
yes, in fact, that's a good way to use this. And we'll get to that later. But right now, if I go through all the different ways, I'm going to see the 6 different ways of doing this. One way of looking at it is the numbers here are all distinct, so it's just 3 factorial. Whereas this is I have 3 factorial ways, and then because I have the 2 zeros that are the same, I have to divide by 2 factorial because I can flip those numbers and they're not distinguishable. This goes back to, if you remember, the Mississippi is a tough word. How do you spell it? How many different ways can you make words from the letters in Mississippi? Maine is a much easier state to work with. Yes, you have to remember there's a silent E at the end, but all the letters are distinct. Whereas in Mississippi, a good way of handling it is you put on labels. First S, second S, third S, fourth S. And you say, well, look, I've got the S's somewhere down, and there's 4 factorial ways to put the labels down on those S's. A much better way of writing this, and I know some of this is not going to be good for kindergarten, is 2 factorial over 1 factorial. Because when you do it like this, now everything on the denominator, it sums up to 3. Everything's been counted. We don't need to do this. We can do this all by brute force. And so now, is there anything else we need to look about? We could have all 1s. Well, fortunately, they're all the same, so there's only one way. Okay, and so this is the same as 3 factorial over 3 factorial, because they're all the same. So we have 3 plus 6 plus 1 is 10. How confident are you on the next one? Pretty confident. So what should the next one be? So the triangle numbers, the nth triangle number, you add n, or n minus 1 to the one before it, depending on how we're defining things. So here things seem to be shifted off by a little bit. So this is always where you have these horrible index games. Is my answer the nth triangle number, or the n minus first, or the n plus 1? I don't really care about that right now. But we've added 2, then we add 3, then we add 4, then we add 5. So sometimes when you're trying to detect patterns, looking at what is your change, the pattern is easier to see in the change than what comes next. All right. So how do we find how many ways there are to write 4 as the sum of 3 numbers? What can we do?
So for people that aren't statisticians that don't know about triangle numbers, I mean, if you tried to just make a simple, it wouldn't be a very simple chart, but it's just too lengthy. I mean, for younger kids,
Right.
would you this factorial? Yeah.
Oh, no. For the young kids, I would not do the factorials at all.
Right.
Absolutely not.
Right.
But I would start saying, do you see a pattern here in these numbers? And we can see this is 2 more, this is 3 more, this is 4 more, this is 5 more.
The next one would be 6 more.
The next one will be 6 more. And so when we have 2, 1, 0, we want to look at how many different ways can we write it. We can write it as 2 plus 1 plus 0, 2 plus 0 plus 1. These are all the different ways with 2 first. Now let's do 1 first. 1 plus 2 plus 0, 1 plus 0 plus 2. Now let's do all the ways with 0 first. 0 plus 2 plus 1, 0 plus 1 plus 2. And
Obviously,
it's going to get significantly more difficult. And what you want to do when you do something like this is you want to come up with a good methodical way to go through things without missing anything. So for instance, I'm starting with the highest and then going to the lowest. You could, of course, also start with the lowest and go to the highest.
I guess I would think about, in our level, we talk about pictures, numbers, and words, and try to put all of that together. So a picture of a triangular number is a number of dots.
Right.
You can make a triangle. So you actually,
So it'll be like this.
and I actually did a pyramid, but that's okay, the same thing. So
Right.
Just create that pyramid, the next pyramid,
Yep.
you're adding another line on the bottom, count the dots.
Right.
So for elementary, they could literally count the dots rather than even knowing, I mean, it's.
Right.
I'm just saying for-
Right, if we knew it's the triangle numbers, yes. So now how would we go through and do all the different ways of breaking up 4? This is the cookie problem. And so, for the people who know a little bit more about the combinatorics, we'll eventually get to the highfalutin way of looking at this. But for 4, I can do 4, 0, 0, 0. How many different ways are there to reorder this?
You have 4 numbers now as well. You want me to do this?
Oh, I'm sorry, 3 zeros. Sorry, 3 zeros. Thank you. So there's 3 ways of ordering this. Now I could have 3 as my largest number, and then the other number has to be 1. How many ways are there to order this? 6. Now I could have 2, and I could have 2 2s and a 0. How many ways are there? 3. And the simplest way is to see, once I choose where the 0 is, I have no more freedom. I could also have 2, 1, 1. How many ways are there to order this? 3. So 6 plus 9 is 15. And so it will come up to 15. It will be the next triangle number. This is going to get very bad if we start going further down. It's going to be very bad if instead of doing 3 numbers, we do 4 numbers. So the question is, can you see a pattern? And so in the previous one, the pattern was clear. 1, 2, 3, 4, 5. You give me n, the answer is n plus 1. There's a formula for the triangle numbers. So do you?
No, well, I don't know it, but anytime that you have 2 of the same numbers is 3. Anytime that you have 2 different numbers is 6.
Good. So we could use that to now start building up. So when we start looking at the next ones.
When I do this with my advanced classes, and I have them since we talk about triangle numbers, I make them make the connection to a triangle.
Right.
Let's talk about the formula for a triangle. there's the whole idea of dividing by 2. So where we're going to embed that into a possible formula now. So I build the triangle upon itself
Right.
and create a rectangle,
Right.
which they all think is a square to begin with.
Well, so this becomes a great way as to, how would you get the formula? And so there is a formula for the triangle numbers. And so there's lots of different ways of getting it. So what we want to do is we want to add 1 plus 2 plus 3 plus n. And so there's a famous story about how to do this going all the way back to Gauss. He had a teacher who was just having a bad day. We've all had that. And the teacher decided to shut the little brats up and just give them a tedious problem to keep them occupied. And so he told them, add the numbers from 1 to 100, expecting that they would then be out of his hair for a while. And then Gauss says, 5,050. And so there's lots of different ways of proving this. My favorite way is to write the numbers now backwards. And so if I write them backwards, 1 plus n is n plus 1. 2 plus n minus 1 is also n plus 1. And I go all the way down to n plus 1 is n plus 1. So the answer is I have n plus 1 n times. But I've double counted everything. So the answer I care about is I divide by 2. So we get that the nth triangle number, so I'll try to write it over here, and then the camera should follow me. So we get Tn is n plus 1 divided by 2. And so in particular, T1, if we put in n equals 1, is going to be 1. T2 is going to be a good movie, and also known as 3. T3 is going to be 6. And so we see it's the triangle number of the next one. Another way to do this, and in fact it's the same as this proof, is we can come back to our picture and we can put in the missing dots to make it a square. And so we put in the missing dots, now we have an n by n square. But what we really want to do, and again we've got to be very careful as to how we're doing the triangle numbers, we've only got the diagonal once. So we haven't quite doubled our number. So if we want to double our number, we also have to add in the diagonal again. So if we do the dot, it's going to be n squared plus n. And then we divide by 2. And that's a geometric way to prove the triangle number formula. Is I've got my picture, I've got my triangular dots, I double it. But if I double it, I have to remember I'm including the diagonal twice. So it's not just n squared dots, it's n squared plus n. And so then, maybe I have these multicolored dots on the side. The other thing is to see what kind of function does this look like. If you're teaching classes on functions, how is this growing? Quadratically. And so what you should hopefully be able to do is maybe, if you have people who are some coders, they could write some code. And again, this is probably not 5, 6-year-olds. When I was volunteering in high school, somebody thought it would be really good to teach kindergarten kids how to program in Logo. And just no concept of what screen size was or anything. But this is a very simple computer code to write. And so I would not worry about writing the code well. For x equals 0 to whatever number you have n, for y equals 0 to n, for z equals 0 to n, if x plus y plus z equals n, then count equals count plus 1. So plus plus is just the shorthand notation, incremented by 1, start off with count equals 0. Okay. This is, of course, overkill. You can make the code a lot more efficient than this. I'm not going to worry about that right now. But you could have people write simple code to count how many things there are and start getting a more populated list. And then as you have the more populated list, can you sniff out the pattern? If you think it's a parabola, can somebody give me the formula for a parabola? Okay. So we're guessing that the answer is y equals ax squared plus bx plus c. Well, we have a lot of data here. We have x equals 0, y equals 1, x equals 1, y equals 3, x equals 2, y equals 6. We have a lot of information. So using this information, we can have a system of knowns. And then we can try to figure out what values must we have for a, b, and c. What's nice is knowing that x equals 0, we have y equals 1, that immediately gives us c. And then you've got to do a little bit more work to get the other values, but. So there's a lot of great stuff you can do with something like this. Now, of course, the question becomes, what if we take it one step further? What if we now have 4 things? What do you think the answer will be?
Something else.
Something else. But give me some idea of the shape of the something else, even if you don't know the exact answer. Cubic. When we had something that was just x plus y, it was a line. X plus y plus z, it was a quadratic. X plus y plus z plus w, because we don't know how to order the alphabet properly, it's going to be maybe a cubic. And then maybe are there interesting things about the leading coefficients in the cubics, in the quartic and whatever? Do you have any prediction of what those should be? And this is the idea where you're now starting to make hypotheses. You're looking at something you haven't seen before. Can you try to sense what the answer might be? And to me, this is the exciting part, is trying to see what the pattern should be before you actually get the data. But of course, in terms of now getting the data, the more things I have, the harder it's going to be to gather the data. And so there's lots of different ways to attacking this. And so what I want to talk a little bit now is using recursion to attack a problem like this. So one thing's, if I was asked to describe a mathematician, I would say a mathematician is a fundamentally lazy object that tries to do as little work as possible and always reduce things to things that have already been studied. Very similar to a politician, where you ask a politician any question, in a debate, very quickly they wander for 30 seconds and then they get into their stock speech, which they were going to say no matter what you ask them. No matter what you ask me, I have a couple of things, a couple of tools, and I always try to work it back to that. So here, we are complete masters at sums of 2 numbers. If I want to do sums of 3 numbers, I want to somehow reduce that to sums of 2 numbers. And so if I can do that, I can then do sums of 3 without too much trouble. All right, so let's look at x plus y plus z equals 10. Well, I can give x plus y a name. Let's call that w. So this is the same as w plus z equals 10. Do we know how many solutions there are to this? How many? There's 11. The problem is, while there's 11 solutions to this, different choices of w have different ways. But you give me a w, how many z's will work? 1. So now, for each choice of w, there's one and only one choice of z that will work. And we'll always assume w is between 0 and 10 so that we don't have to worry about overflow. So once I know how many ways there are for a given value of w, I only have one choice for z. So now I just go through the different possibilities of w. How many ways are there for w to be 0? How many ways? 1. For w equals 1. For w equals 2. All the way down to w equals 10. So I now have to add all this stuff up. And so if I add them all up, I should get, I think 11 times 12 over 2 is, I think, 66, if it works. And so this is now reducing a new problem to something we've done before. And to me, this is one of the fundamental concepts in mathematics, is you want to reduce a complicated problem to a simple, yeah, that's how we do it. And now that we have a formula for sums of 3 numbers, we can now do sums of 4. So you can't have a math class without homework. So for homework, try to think how you would do sums of 4. There are two possible approaches. Can somebody give me one approach to try to do sums of 4?
2 and 2.
One is 2 and 2. And what's the other one? 3 and 1. So this now comes down to parentheses. You know, why do we care about parentheses? Why do we care about orders? Well, I can either view it as x plus y plus z plus w, or I can view it as x plus y plus z plus w, the associative property. Now what's nice about this is this breaks it down into two simple things, into two nice things, but now I have to multiply. This breaks it down into, w is now very easy, but now I have to deal with sums of 3 things. And so what I like about this is there's not one right approach to a problem. Depending on what you're doing, different ways will give you different advantages. And so there's a lot of stuff you can do from this number bonds. What I want to do now is I want to jump to the optimal solution, to how you would do this in general. And this uses a little bit of basic combinatorics. So how many of you do not remember the combinatorics, n choose k, n choose r? Okay, this is when you have n objects. How many ways are there to choose k objects from n when order doesn't matter? So I will quickly review that, and I'll show how that can completely solve this. And then I will give the connection to tic-tac-toe. Okay, so let me just make sure I'm in focus. Oh, I'm so good. I'm still green. Good. So n choose k is n factorial over k factorial n minus k factorial. This part is, sadly beyond most, kindergarten classes. This is the number of ways of choosing choosing k objects from n when order doesn't matter. So think of it as you're choosing people to be on a committee, and all posts on the committee are the same. You're not choosing the executive board. One of the best definitions of the vice president is you die, I fly. There's a difference between being vice president and being president. Okay? There's not much of a difference being student counselors. So in terms of just trying to put this into context that students would see. If I want to know how many ways are there to arrange people, that's just the factorials. How many ways can I arrange 5 people? It's 5 factorial. 5 times 4 times 3 times 2 times 1. 5 times 4 times 3 times 2 times 1. What if I only want to arrange 3 of the 5 people in order matters? How many ways can I arrange? 5 factorial over 2 factorial. So the answer would be 5 times 4 times 3. And then one of the things we love to do in mathematics is we love to multiply by 1. It's one of the few things we know how to do. And you can multiply by 1 without changing the answer, but now the numerator becomes 5 factorial and the denominator becomes 2 factorial. So this is the number of ways to order 3 people from 5. Well, what if I don't want them ordered? So here, president, vice president, pizza guy. Okay, my 3 most important positions. And for those of you who may be laughing, and I know this is being recorded, when I was an undergraduate at Yale, we created the position of secretary to the Yale Math Club, whose job was to provide pizza. And this was held by a chain of pre-med students who wanted to increase their chances of getting into a good med school, thought it would look really good to say secretary of the Math Club as an extracurricular. And so their job was to provide pizza. We got someone to do the dirty work. They got a line on the CV. It worked out really nicely. Those 3 positions were not equal in terms of prerequisites and abilities. Can we remove structure? It's very easy to remove structure. Just forget about it. And so I have 3 people now, and now Alan, Bob, Charlie is different than Charlie, Bob, Alan. How many ways can I order 3 people? That's 3 factorial. So if I want to kill the order, it's 5 factorial divided by 2 factorial divided by 3 factorial. And this is the 5 factorial over 3 factorial, 2 factorial, and it's the same as 5 factorial over 2 factorial, 3 factorial. And depending on what people are interested, we can talk a little bit more about this. So this is one of the big building blocks in combinatorics, the n choose k. So I want to show you how this solves the problem we were doing about the number bonds. So the way I like to phrase this is I like to do it in terms of what I call the cookie problem. So imagine you have 10 identical cookies and 5 hungry graduate students. It's actually a little bit redundant to say hungry when you're talking about graduate students. It's almost a given. I will assume the graduate students are distinguishable. So I'm not talking about something like electrical engineering or lab science. We will assume that the professor can tell the difference between their graduate students. Okay? The question becomes, how many ways can I divide the 10 cookies among the 5 grad students? And the cookies are identical, so you can't tell the difference. You know, these are not like normal Earth cookies where my kids will be able to detect very small, minuscule, infinitesimal. These are perfect cookies, all identical. Is this problem well defined? How many ways can I divide 10 cookies among 5 people?
Are you using whole cookies?
So using whole cookies. So I'm not allowed, so these are important things. I am not allowed to split a cookie in half.
Are you dividing them equally?
I am not requiring myself to divide them equally. I'm not even requiring everybody to get a cookie.
Some people may not get any.
Some people may not get any.
Somebody could get all 10.
Somebody could get all 10. We call them the professor. When I was a postdoc at Brown, there was a free food email list where the grad students would email each other. You know, there was a talk at 4 o'clock in the following building, followed by, and they would describe the food. And the graduates said, yeah, I can listen to that for pizza. Wait, I'm just going to get some crackers? No, I'm not going to spend 45 minutes for crackers. So 10 identical cookies.
Ungrateful but biteable.
Yes. 5 distinct grads. So how could we go about this? 5 variables at 10. We could do the big tree we were doing before, the number bonds, with 5 things. We could go 10, 0, 0, 0, 0. And then 9, 1, and looking at all those possibilities. And then by the time we get to the 4, 3, you're going, I chose to sign up for this. There's a way to do this in one line. Anybody a fan of the original Sesame Street? There is a character who has caused some of the original episodes of Sesame Street to lose their G rating. No, it's not the Count. It's the Cookie Monster, because the Cookie Monster encourages unhealthy eating. I was also told that Oscar the Grouch now lives in a recycling bin, and I will admit they got me on that one. Sesame Street has not gone that far yet. But I need the original classic Cookie Monster. And what can you always count on the Cookie Monster for doing? Eating cookies. Well, see, that's one of the problems. You have to make sure you only eat some of the cookies.
Well, he loses a lot of cookies.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Imagine we have 14 cookies. And Cookie Monster comes, and Cookie Monster very happily eats 4 cookies for us. These cookies are gone. And we somehow stop the Cookie Monster after this. There's 3 cookies up to the first eaten cookie. Between the first and the second eaten cookie, there's 0. Between the second eaten and the third, there's 2. Between the third and the fourth, there's 2. And the last, there's 3. 3 plus 0 plus 2 plus 2 plus 3 equals 10. It turns out there's a 1-to-1 correspondence with the number of ways you can choose 4 cookies from 14 when order doesn't matter, and the number of ways you can divide 10 cookies among 5 people. This is all starting from the number bond problem. So I'm trying to find something that goes for all the different levels depending on what background your students have. And what I like about this is this brings in the word efficiency. It's not enough to solve a problem. This is not a hard problem. With enough time and patience, we can solve this. We don't want to have enough time and patience. This is not fun, to go through and do this by brute force. And you look at all the different ways. The answer is just 14 choose 4, which is 1,001. And so now we can go back and we can see in a very unified way how to solve all the other cookie problems as well. If we have x plus y equals n, what's going on? Well, really, the answer here was we looked at the number of cookies plus 1 less than the number of people, and we chose the number of people. And by putting in here 4 partitions, we split our set into 5. So now, if I want to do x plus y equals n, instead of having 5 distinct grad students, I now have 2 grad students. So the formula should just be n plus 2 minus 1, choose 2 minus 1, which is just n choose 1. Oh no, n plus 1 choose 1. Good, perfect. I was about to say that doesn't work. N plus 1, which is just n plus 1. If we have x plus y plus z equals n, this now becomes n plus, now we have 3 people, minus 1, choose 3 minus 1. This is now n plus 2, choose 2, and that will be the shifted triangle number we need. And so you can now see a unified approach to all of this. So I really like the cookie problem. I've used this actually a lot in my research in terms of number of ways of counting decompositions. And again, one of the things I love about this is we're counting things efficiently. We're finding a way through all the brute force. We're seeing big patterns. It also introduces this idea of recursion, of reducing a complicated problem to lower cases. Okay? Now the question is, how is this connected to tic-tac-toe? Before getting into tic-tac-toe, I can either go straight to tic-tac-toe, or I can talk about lines of symmetry first, which then go into tic-tac-toe, or use tic-tac-toe to go to lines of symmetry. I know some of you have been waiting to learn how to play tic-tac-toe. Any preference? Tic-tac-toe. All right. So tic-tac-toe is one of the greatest games of all time. How many opening moves are there in tic-tac-toe? 9. So there are 9 opening moves. How many responses are there? So if I want to look at all the possible games with just 2 moves, there's 9 times 8. How many responses are there to the response? And then responses to that. Responses to that. Responses to that. Good. Yes. At this point, we could have the March of the Morons. X, O, X, O. So if you want to just make simple count, how many games of tic-tac-toe are there? Unfortunately, at some point, well, we have to worry that the game is over. You can keep playing if you want, but the game is over. If you look at a best of 7 series in baseball, once a team has won 4 games, oh, well, let's just play the last games just to see what happens. No, they're celebrating, the series is over. So in terms of analyzing and just counting something as simple as how many games of tic-tac-toe are there, that is not an easy question. It would be much easier if we allowed the game to continue. I also teach a course on Legos, and so this connects very nicely to something like that. How many ways are there to combine Legos and build different structures? So I had the game where we were marching up like this, X, O, X, O, X. Is that the same or different than this game? X, O, X, O, X.
It's different in your counting.
It's different in my counting. It counts as a different game. It's the same pattern. If I had a giant mirror over here, they're the same. So in terms of trying to decide what you care about, do you care to count these as the same or different? They're physically different games, but they're different moves. And again, they could start off like this, and then at this point, I could realize, oh, wait a minute, I should go down here and not here. And so they could start off differently, and then because of how the game unfolds, end up different.
They're redundant because of the number of moves it takes to end the game.
If this is the actual pattern that happens, the games are in some sense equivalent. And so you can use this to now start talking about the notion of equivalency. Everybody has seen equivalency. It's about 10 o'clock now. What time will it be in 5 hours? So 10 plus 5 is 3. Well, considering that you thought 12 over 24 was 1/2, I'm not surprised. But so students have already seen something like this when they've looked at clocks. That what we're really caring about when we look at clocks is just how are you up to multiples of 12. That's what really matters. When we're trying to analyze something like this, for the purposes of the game, these are equivalent. What's wonderful is, if you're teaching especially upper level kids, you can talk about some things from chemistry and biology. I think it's called chirality. There are certain chemical compounds where their mirror image would be very deadly to you because of how it will interact with your body. And so my spelling is atrocious. I think it's chirality. My pronunciation is even as bad as my spelling. But in terms of just trying to see why you might care about something like this, for some things, it's not enough to be equivalent under a transformation. The other question is whether or not it's a transformation you can physically do. So if you look at these two games, where, remember, we looked at the very special ordering where in the first game, purple was going up, and the X's and O's were going up, and in the second game, they were going down. What if instead I did the following? X, O, X, O, X. Is this equivalent or not equivalent to these other games? Equivalent. It's a rotation. Which do you think is more equivalent? This and this, this and this, or this and this? The two on the top. Because I can get from here to here by just rotating, and I'm staying in the plane. Whereas to get from this one to this one, I have to physically go through three-dimensional space. And so it's very different to get from here to here. But again, this is where you have wonderful things to talk about with the students. How do we classify? What metric do we use? In terms of counting, do we want to count these the same as different? In terms of analyzing the game of tic-tac-toe, at the end of the day, do you really care if you have to flip this through 3 dimensions? No. And so for our purposes, if we just care about analyzing the game to win, we don't care about flips. So how many opening moves are there for tic-tac-toe? Corners, middles, and side. There's really only 3 opening moves for tic-tac-toe. The corners are all the same. The sides are all the same. And then we have the middle. So which square do you think you probably want to go in if you're opening? The actual answer is doesn't matter. If you're playing a good person, it's a tie. What I like about the middle is if you think about all the different ways to get 3 in a row, the middle is involved in 1, 2, 3, 4. Nothing else is involved in 4. The corners are involved in 3. The sides only the middles are only involved in 2. So it almost seems like maybe the best opening move is to grab the middle. This leads to the concept of something that might be locally best, but not globally best. And so one of my favorite examples, and I know this is a bit over the map, do dogs know calculus? And so I've actually met the dog in this story. So imagine you're in the water with your dog, and you throw the dog a stick. What path does the dog take? I throw the stick over here now. How does the dog swim? Throw the stick all the way over here.
Where's the dog?
Dog's right here.
Oh, the dog.
Did you say in the water?
Yes, in the water.
There it started, yeah.
This is the water.
The next one.
Yeah. I've got blue, so here's the water. And here is the beach. If any of you teach calculus, anybody here teach calculus? Do you ever do the drowning lifeguard problem, drowning swimmer problem?
We do other optimizations.
Okay. So how should the dog swim to the stick now? I'm sorry?
Go to the beach.
Go to the beach. The dog should go at some angle to the beach, run along the beach where the dog is fast, and then come back up. And so, I know if you Google Tim Pennings, and the dog's name is Elvis, there's video and there are a couple of papers about this, where he's actually taken his dog into the lake and looked at the path. I'm sorry?
What breed of dog?
I'm
A
not.
lot of swimming experience.
Right, the other ones didn't survive. So, but there's some good video about this. And what the dog has realized is that what is best locally is not always best globally. If you want to look at, a few seconds later, what path should you take to be as close as possible to your destination? Well, the best thing you can do is go straight for it. And that's the best thing you can do if you only care about, I want to be as close as I can after 1 second. But that's not the goal. The goal is not to be as close as possible after 1 second. The goal is to reach the stick as fast as possible. And it's better to take a little bit of a hit and go to land, where you can then run much faster than you can swim, and then come back into the water. So I love this example to talk to students that when you're trying to figure out what your strategy is, doing the best thing at each moment, while that seems good, it may not be the best thing to do.
You ever start when you're throwing the ball from the beach at different angles, and then the dog runs along the beach for a certain distance and then swims out? Like if you ever had a
Right.
on the beach, you throw it off at a 45-degree angle, the dog doesn't
Yes.
swim straight for 45.
The original stuff was like that, with the dog starting here and somebody throwing the stick into the water, and the dog would run
Yeah.
and then jump at the right point.
Yeah.
Yep. And so there's lots of great stuff here, lots of great lessons. But now in tic-tac-toe, there's only 3 opening moves. So now in move 1, either X goes in the right corner, sorry, I guess it's the left corner, in the middle, or I guess now we have the middle. All right, now we have to respond. How many ways are there to respond to a move in the corner? Okay, why 2?
Because the corners are considered one move.
Okay.
So you have the sides of the move.
Okay, but are all the sides and middles the same?
No.
Relative to the X.
So,
And if you say you're either next to
There's really
it or
only
you're
two
not
places
next
you
to
would
it.
go.
that's if you're playing intelligently. One of my advantages is the elementary school kids do not always play optimally. So how many moves do the elementary school kids have? So they have 8, but we want to trim that down a bit.
For 2, 5.
I mean, they're either next to it or they're not next to it. So.
Okay, so these are 1. What else is equivalent to that corner?
The top right.
The top right, 2. Then this would be 3. Then these 2 would be 4. And then this would be 5. So there's 5 responses. If I look over here, I have 1 response by going into an adjacent corner, then 2 responses down there, 3, then these corners, 4, 5.
Why is the center not considered a 1 under that scenario?
Well, because this is not the same as this move.
But you're still blocking a direct path.
What I'm saying is,
The board state's going to be.
if I look at this,
Okay.
right,
I got you.
right, these are not equivalent.
Yeah, because of transformation.
Because of transformations. There's no way to just rotate, reflect, and get these 2 to be the same as each other. So there's 5 possibilities here, 5 possibilities. How about here? 2. So I have the 4 corners and the 4 middles. So 5 plus 2 is 12 versus 9 times 8, which was 72. So it's a factor of 6 savings in terms of just looking at the possible game plans.
So it's better to do the first 2 because there's the 4s are both bad moves, and there aren't any bad moves.
Are you talking about in terms of for
In
X?
terms of a strategy, is it better to play one of the first 2 because they might make one of the bad moves?
So this now leads to a phenomenal question. What if you look at all possible games of tic-tac-toe where people move randomly, and you're as likely to take any open square as possible? How often do you just happen to win like this?
If they take 4, you're much more likely to win.
Well, but this is where, in terms of phrasing a good question becomes very important. Are you playing against a bad opponent who, if they move here, you can now take advantage and win? Or are you worrying about that you're going to be playing against a good opponent? Or are you both just equally bad and you're just both and just, filling in squares randomly? And if you just fill in squares randomly, what's the probability if you randomly start off here that you win versus you win if you randomly start off here versus you randomly start off here? We can now start analyzing. If we look over here in terms of our possible responses, in this situation, if I go in 2, I'm going to lose. So now, if the board looks like XO, there's lots of different ways for X to win. The main thing is you always want to be forcing someone to move in a certain way. You want to attack 3 in a row 2 different ways. If I go here, this now forces O to go up above. So one of the things that's nice is in game theory, if you can force someone to move in a certain way, you have enormous power. And now, if I go over here, I'm attacking 3 in a row 2 different ways. So in terms of the game plan for here, if X goes here, I can't go there. And so you can really start to prune the analysis in terms of if I don't want to lose, which when I'm playing the elementary school kids, I have my reputation, the analysis is not so bad. And so this leads to how do you quickly go through all the different possibilities of tic-tac-toe? This is the idea of efficiency. When you start looking at 9 times 8 times 7 times, that's a lot of different things to look at. If you watch football, some quarterbacks have things written down on their arms. I do not go to the elementary school with tic-tac-toe strategies here. I'm not pulling out my smartphone and checking what ways to do things. It's what calculations can I quickly do in my head and see what's going on. Okay, most of you I think have played tic-tac-toe. By now I think tic-tac-toe is boring. What could we do to make the game interesting?
Make it like a 4x4 grid.
So one thing is to make it by a 4x4 grid. Now, do you need 4 in a row?
I guess.
Maybe it's still 3 in a row.
So the grid is 4x4, but you can get 3 in a row to win.
Well, so
Or you turn it to connect 4,
Next 4.
or you make it 3D.
so one possibility is making it 3D. But you've got to be careful. Let's imagine you have a huge board and you only need 3 in a row.
Like Connect 4?
Like Connect 4, but now you just need 3. Now with
Only built up from the bottom, so that's
right, Connect 4 has that interesting twist. So if I go here, if opponent responds over here, I go over here now and I win. So if I go here, opponent has no choice. They've got to go here to block me. I go here.
now you win.
And now I win. So if I have a large enough board, getting just 3 in a row is not going to be that interesting. So
Tic-Tac-Toe is even more boring.
unless you get to go first. But so this becomes an interesting question. How do you find a fun game? So one thing is, I have a certain size board and I have to get a certain number in a row. Would you rather go first or second? First. So what you could do is you could actually pre-fill some squares on the board with O's, maybe away from the center, so that if the person who's O can survive for a long time, they can actually then get to some of the O's that are out there. So there's lots of tweaks you can do. You can play tic-tac-toe on a torus, on a donut, where you wrap around, or on a sphere. Try to change the geometry. But try to get the kids to find a fun way to do it. There's 2 other versions of tic-tac-toe that I know of that are interesting. One of them is gobble tic-tac-toe, or Russian doll tic-tac-toe. So you have 2 large pieces, 2 medium, and 2 small. The large can gobble the medium can gobble the small, the large can gobble the small. And on your turn, you can either place down a new piece or cover a piece already on the board. And you can even cover your own piece. And so now, of course, the big pieces are very valuable. You sometimes want to hold them in strategic reserve if you really need to win a square. You could put down a small piece, somebody takes over the square with the medium piece, and then you take it back with a large piece. You could even allow, maybe you can remove a piece that's already on one of your pieces and free up something underneath. And you have complete freedom, what leads to an interesting game. The other version of tic-tac-toe that I like is called bidding tic-tac-toe. And so there's 2 ways to play bidding tic-tac-toe. You love to gamble with your students, right? So each person starts off with $1,000. and we'll assume you can bet any real number. Whoever bids highest gets the first move. And there's two versions. In one version, when whoever gets the move, you give the money to the banker who's not playing. In the other version, you give the money to the other player. Let's play where you give the money to the other player. So you really want that first move, you bet $900. I bet $200. You win, you get the first move. You're now at $100, and I have $1,900. And so you got that first move, you go in the middle. How much do I bid for the next move?
$101.
I could do $101. I could do even less if I want to, because if you want to deplete your resources even more to go against me, that's fine. I'm just trying to get 3 moves in a row. $101 would be fine. So I bid $101. I outbid you. You go up to 201. I go down to $17.99, and I'll go here. On my next turn, I'll bet $202. You'll be around 400. I'll still be more than double your score, and I'll keep going, and I'll get 3 in a row. And so now in bidding tic-tac-toe, you want that first move, but how badly? And so this is a great way to take something that hopefully your students have seen many times and put a twist on it, and have them try to figure out how much is that first move worth? How much do you really want to bid for it? And so, there's some strategies online. They can try to play against you. They can try to play against other people in the class. Marbles. And so this is a lot of really nice game theory. And so in terms of why do we care about stuff like this? You can start talking about competition between companies, competitions between countries, trying to find optimal strategies. And you have a certain amount of resources. How do you want to use them? What are the consequences of using your resources? You sometimes want to keep a strategic reserve for emergencies. I know this is being recorded, which is why I want to talk about the horrible experiences I've had flying with United recently. Multiple times they've been canceling planes on me. What airlines like to do, if possible, is have a strategic reserve of planes so that if a plane goes down for mechanical reasons, they have another plane they can just bring in immediately to service. What's the problem with this? It's costly, right? You don't want your planes sitting on the ground. You want your planes flying people. The more planes you have on the ground, the fewer flights you can do. Where do you want to have your planes? In the air. But if you're going to have them on the ground, where do you want to put them? Your hubs. Busy airports, hubs. Which hubs? Probably the hubs that have better weather. Right? So you don't want the planes grounded because of a storm. You want the planes to be able to move through the network. So it becomes an interesting question. Where do you put your planes? What fraction of your fleet do you want to have in reserve? You can talk about banks, and banks have to have certain amounts of cash reserves to meet certain types of calls. This now fits in beautifully with tic-tac-toe. Player 1 was too gung-ho, and he bet so much in the beginning, he did not have enough to deal with the situations that unfolded later. And so, again, the whole idea of trying to figure out, where am I going to use this? Why do I care about all this? We started by looking at, number bonds and how many ways can we write, 10 as a sum of 2 numbers. And from that, we got to a lot of really interesting math lessons. We got to see some statistics, some pattern recognition, and to me, this is one of the most important skills we can teach our students, is how do you recognize a pattern? How do you gather data? How do you analyze data? How do you look at the appropriate data? It's very easy to manipulate data and give people false impressions. One of my favorite examples, Henry told you what my best qualification was for teaching this course, which is I'm a Red Sox fan. So in the last 5 days, the Sox are, well, let's say the 3 of the last 4. Are the Sox playing well or not? They've won 3 out of the last 4 games. 75% winning percentage. I'm sorry?
Depends on how good the team they're playing was. Better than those teams.
Better than those teams. But I mean, if you hear the team has won 3 out of 4, do you think the team is playing well?
Yes.
For that period of time.
It's only 2 teams.
Well, I mean, or if you want to think football, we'll think football. Pats. All right, so the Pats have won 3 of the last 4. Are the Pats playing well?
Well, that
Yeah.
changes the context, actually. because
It does.
Football season being much longer than football season.
Yes.
162 games versus what, 12?
And
10 times
if
longer.
you have a 3-game homestand against one team,
We're just looking at the numbers. 3 out of 4 is a drop in the bucket. Right?
Well, but I mean, this is like the do dogs know calculus. This is a local question. How are the Red Sox, how are the Patriots doing locally? Are they playing well or not?
Yes.
What happened to my team 5 games ago? They lost. Oh, how do you know they lost?
Because they've only won 3 out of the last 4.
If they had won that game, what would I have said? I would have said they've won 4 out of 5. So if I'm saying they've won 3 out of 4, you know 5 games ago they lost. This is manipulating statistics. So for those of you who are teaching statistics, there's some great clips. I can send you a clip from one of my favorite TV shows, Yes, Prime Minister, about just how easy it is to manipulate statistics. Do we know anything else? We know they lost 5 games ago.
You know they lost one.
3 out of 5.
The
They
next
lost
game they lost to.
Which game did they lose?
The next one they're going to have, right?
the 3rd one, probably.
Is it
Well, I mean, if you know what's going to happen in a game that hasn't been played, see me after class.
I can tell you the score before the game.
Well, it's either the 2nd or the 3rd.
I mean, is it implied that's not a 3-game winning streak out of those 4?
It implies there's not a 3-game winning streak, because if they had won their last 3 games, we would have said they've won 3 in a row. So what do we know had to happen in game 4?
A win.
Has to be a win. Has to be. And so now in games 1, 2, and 3, we have 2 wins and we have 1 loss. An average team should win 1.5 games out of 3. You know, they've won 2 out of 3 or 3 out of 5. 3 out of 5 is 600. So, you know, all of a sudden you go from a team that's winning 75% of their games to winning 60%. Well, you expect them to be winning 2.5. There's really no statistically significant difference at all. But you can make it seem so much better. So in terms of the importance of how you present information and you're being able to look at data, this is a great skill. And so I'm trying to think if there's anything else I want to just say about this. So we talked about the cookie problem, about the combinatorics in terms of counting things efficiently. It turns out in computer science and mathematics and number theory, frequently you want to look at how many ways we can decompose something. And these combinatorics, these gives you lots of great ways of doing something like this. One of the difficulties is always, how do we know we found everything? You know, how do we know we haven't missed anything? This is the bane of all combinatorial things. And so we'll take a break in a few moments. When we come back, I want to talk about lines of symmetry. And then applications of something like that. Again, trying to start off with something you would do in kindergarten and going all the way up to something you would do in college. So a lot of this is, college and beyond. This is related to research I do, but just trying to give you, things on a whole different sense of scales. Okay.